No, my claim is that they won't come in at any order of perturbation theory. They don't come in around these backgrounds. Yeah, well, that's what this question is. So I have some complicated expression here that's got lambda, again, coupling for curvature squared, coupling for curvature cubed. There's also the ADS, or the scale in the cosmological term, or in the potential. That's the dimensionful scale. And then this was sort of an extra parameter that said which stationary point I was at. You know, this is a complicated formula, but it's all in terms of the gravitational theory. What did I learn about the boundary theory? So you might ask, is this central charge something that we understand? Well, in the four-dimensional case, when D was 4, we understood that at the stationary points, this was actually the central charge A. But now in general dimensions, I don't know what the answer is. Oop, I'm going the wrong way. One thing I can say, though, is that this is not this particular central charge, which is common. That's something I could define for any dimension, a conformal field theory. And I know that, well, I can just compare, and I find that this is not that. I might have expected that because in 4 dimensions, it's C that appears here, not A. And so already in 4 dimensions, that wasn't working. It's also not, you know, I can think about a thermal ensemble, and there's, you know, some nice charge here, say in the entropy density or the energy density, that tells me, you know, that's giving me a count of the number of degrees of freedom. But again, I can just calculate, and because I have the black hole solutions, and I know that this charge or this quantity doesn't match that formula. So again, well, this is saying some things that it's not. Saying something that it is, if I go to the case of even dimensions, in even dimensions, there's always a trace anomaly that in arbitrary even D, and it has some general structure that looks like this. There are terms that basically involve the Weyl curvature, and then there's a special term that involves the Euler density in that dimension. And what we find is that this formula actually corresponds to the coefficient of this particular term. And that's why we have all these ugly factors here, so that we get things matching up precisely. So that's an interesting result, because Carty actually said, or his conjecture actually applied for any even dimensions, and it's this central charge that he was focused on. And so our holographic models then are giving us support, or giving support to that proposal in any number of dimensions, or any even number of dimensions. And in fact, that connection applies for all of these examples that I mentioned on the previous transparency. But again, we have the question, you know, D is just a dial in our calculations. What does this mean for the odd dimensional field theories? So there we were actually puzzled and were stuck for a while, but this is where the story of entanglement entropy comes in. And so this is the story that I told, although I probably rushed through it yesterday, where I'm calculating the entanglement entropy in a d-dimensional CFT in flat space, but I'm choosing the entangling surface to be a sphere of radius r. And it turns out that there's a universal contribution in that entanglement entropy, and at the bottom here, what we're saying is the universal contribution I can match up, and I can see it corresponds to this gravitational, in the gravitational or in the holographic context, I get precisely this combination. But again, just to run through the words here, the way that we established how to calculate in the holographic context is I set up this problem, then I use the conformal map, or I use the conformal symmetry here of the theory, and we do a mapping to some other space where our entanglement entropy calculation turns into a thermal entropy calculation. Then we use the holographic dictionary to say thermal bath, black hole. And so our original entanglement entropy is equal to the horizon entropy if I'm doing the ADS space, and I find the appropriate black hole. Turned out that black hole was actually just a particular foliation of ADS space, the so-called ADS Rindler coordinates. But then, you just take the usual gravitational technology, you evaluate the horizon entropy, and then you find that this is the universal contribution. And what's appearing here is precisely that AD star, that complicated formula that we had for the gravitational, or for the thing that was flowing in our C-theorems. And so what we're saying is you can, in any number of dimensions, you can look at this problem of calculating entanglement entropy. That will let you identify a certain quantity in a CFT. And if I think about RG flows connecting two CFTs, I'll find that that quantity is always bigger at the UV end than it is at the IR end. And this then is a discussion or a framework that unifies both odd or even dimensions. People never talked about C-theorems in odd dimensions before, but here, because D was just a dial, we have one framework, entanglement entropy, and we're talking about these flows in odd or even dimensions. I said that this corresponded to A, or it corresponded to what this flow, or this inequality corresponded to Carty's conjecture for even dimensions. So it's not really new, but it's giving a new perspective on that conjecture in that we're talking about it in terms of entanglement entropy. And, well, perhaps being bold or foolhardy, although we discovered in the holographic context, what we conjectured is that this kind of flow or this inequality should apply generally outside of holography. So that was the end of, that was the end of holographic C-theorems. No, it was the end of 3, okay. And so then I wanted to go on, but that slide means that I'm supposed to pause, look at the audience, and ask if there are any questions. Okay. I get to go to the end, right? Sure. Oh, so in general, there are, like there's an area law term, there's all sorts of terms, and I'm just focusing here on the universal contribution. Yeah, well, that was part of yesterday's discussion, but no. Oh, well, okay. Okay. Well, yeah, there is a way that we took that into account. I mean, well, you see, for instance, here's the cutoff appearing in the log. Okay, so that was, so we started in holography. We saw entanglement entropy was an interesting way to think about C-theorems, and now we're going beyond holography. So our friends in Princeton, soon after, were playing around with quantum field theories. In particular, they started with supersymmetric gauge theories. And what they did is they examined, I take my conformal field theory, I put it on a 3-sphere if I'm in 3 dimensions. I evaluate the partition function. There's some universal contribution that they call F because it looks like, well, a free energy. And what they showed was in all their examples that this was something that had a nice monotonicity. That if there was an RG flow connecting two of these theories, it was always larger at the UV end than at the IR end. And they went beyond that to think about, well, various other examples that weren't supersymmetric, for instance, and this still applied, and so they made the conjecture that this should be a general statement. And in fact, this kind of discussion extends easily to any odd number of dimensions, not just 3, but 3 will be the focus of our discussion. Something that I had actually shown before their paper came out was that this approach, evaluating this partition function, and the entanglement entropy approach were actually one and the same, that we were identifying, or that what they were identifying was the same thing that we were identifying with our entanglement entropy calculation. Oh, and so I guess I'm going to explain that, but we're running a little bit late. Can I can explain it? Okay. Okay, so I'm thinking about the entanglement entropy. That was for a d-dimensional CFT. I'm thinking about a spherical entangling surface of some radius. Again, it's a CFT, and so I can do a conformal mapping. Again, what is it that I'm mapping? I'm looking at the causal domain. I'm not just looking at this spherical region or ball-shaped region in the time slice, but I'm looking at the causal domain that grows out of that. And there is a conformal mapping that takes it to the static patch of de Sitter space, where the curvature of my de Sitter space is given by the radius here, and the temperature of my de Sitter space is also 1 over 2 pi r. So the density matrix there, in principle, I can write like this. And again, what I've done is I've translated my entanglement entropy, or in principle, my entanglement entropy gets translated to a thermal entropy. Now it's the thermal entropy that I see from the Hawking radiation from the cosmological horizon. In general, that takes a form like this. There's, well, this is just thermodynamics. There's a beta energy term, and then there's the free energy term, or the log z term. If I'm in an odd number of dimensions, well, okay, no, okay, I guess. This term I can fix using the trace anomaly, but something that's true is the trace anomaly vanishes in an odd number of dimensions. And so this term goes away, and it says that my thermal entropy and the partition function are actually simply related. And so that says that if I focus, oh, yeah, okay, why is this thermal entropy the same as this partition, or why is that interesting? Well, if I go to the Euclidean, where I usually do my thermal calculations, the Euclidean version of this de Sitter geometry is actually just a sphere of d dimensions. And so what I'm establishing here is that this entanglement entropy and that partition function on the sphere are the same for any odd number of dimensions. A slight subtlety there is that I'm actually focusing my attention on the renormalized quantities, or the universal contributions. In fact, you might find divergences, well, you do find divergences here, but you also find divergences on this side. And if you think about it for a while, the divergences, the divergences don't match. But when I said things like this is equal to 0, implicitly I had thrown away, or I had renormalized the theory and eliminated the divergent contributions when I said I'm focusing my attention on the trace anomaly. So this result is really a result about the finite or the universal contributions in the F and in the entanglement entropy. And again, it's something that applies for any number of odd dimensions. It's really, I use conformal invariant, so it's really only an equivalence at the endpoints, but again, that's all we really needed. If I can, well, yeah, if I want to establish this inequality, the inequality referred to the endpoints, and so that should be good enough. What was even more exciting, though, however, was that our friends Cassini and Huerta came in a year later, and they actually were able to use the entanglement entropy approach to establish this F theorem. And so this is the place where I draw pictures, but I don't really tell you what goes into the proof, because the geometry, well, what the pictures are supposed to do is just convey that the geometry you're talking about is far more complicated. But at the end of the day, they identify, this central charge, and they show that it's bigger at the UV end than at the IR end. And again, I just use that word, central charge, but it's not a central extension. I'm just using it as, that's my nomenclature. So that I'm flashing, but I'm not really explaining. You might think, wow, I've got a new way to think about C-theorems in any number of higher dimensions. I mean, certainly we said you could identify this interesting charge in holography that satisfied a certain monotonicity property in any number of dimensions. But unfortunately, their proof of the F theorem doesn't really extend to higher dimensions in a simple way. Turns out the geometries are even more complicated in higher dimensions, and you get new kinds of divergences, and in some sense you trivialize this inequality, by which I mean that when I talked about it before, I said that the first order term was 0, the second order term, or no, well, the 0th order was 0, the first order was 0, the second order was where I got an interesting inequality. In higher dimensions, you're expanding to higher and higher orders, and it turns out that one of the terms in your expansion is something that is just obviously positive. In fact, it's positive infinity. It's not canceled out, and so you're not getting something interesting. What else do we have to say? Oh, that's okay. This is beyond d equals 3, so I should mention that d equals 4, the A theorem, was actually proved by these folks here, Komagardsky and Adam Schwimmer, but they used a completely different technology, something more familiar, or something I might call more standard tools from particle physics or from quantum field theory. Again, I'm not going to go into any detail about this, but we can talk about it later. Certainly nowhere on this transparency is there any entanglement in sight. Okay, we can't take the entropic one beyond d equals 3. D equals 4 seems to be working with standard techniques. Solidukin proposed in 4, maybe there's some kind of hybrid approach that uses ideas here and entanglement entropy, but that's still a work in progress. There's certain problems with that. You know, we would like to go beyond d equals 4, but it seems in both cases we need a new idea. But it's an interesting question. Can you prove some kind of C-theorems for d equals 5 or d equals 6%? So that takes us to the end there. I'll pause briefly and ask if there are any questions. Okay, so now we're going to go beyond entanglement entropy. The first question is, why is the universal term universal in my discussion of the entanglement entropy? In particular, these folks complained to me very shortly after we put out our first paper, and their intuition is that, you know, in particle physics, when I'm calculating, you know, things like cross sections or scattering amplitudes, log divergences tell me something physical about the theory. But I can find also contributions that are finite polynomials of the momentum, and those can be subject to renormalization ambiguities. And so finite terms like that aren't seen as physical, or they depend on details of our regulator, if you like. So here I've got a log divergence in an even number of dimensions, and so that seems okay. In particular, in previous talks, we've seen various expressions like this, and we see that there are coefficients that depend on central charges and lots of geometry, so that seems okay. But then this is just a finite term, in particular in 3 dimensions, and so that might be, there's a problem there. In particular, if I were to think about shifting my cutoff from whatever value I chose, if my grad student chose a different value that happened to differ by something like this, then the constant term here would get polluted by all these higher order terms that appeared in the entanglement entropy. So that seems bad. On the other hand, I said that if I'm sitting at a CFT at a critical point, that's a place where there are no other scales in the problem. So where did I get this m to make this formula dimensionally correct? So maybe at the critical points, that's not a problem, and this really is universal. However, the other day, we saw that that's not really true. If I have an RG flow that takes me down to a CFT, scales that appeared in the RG flow can appear in the final answer for the entanglement entropy, even in the infrared. So that was something, well, I originally learned it from a paper by these folks, but we saw it the other day in one of the talks here, where there was an m squared term appearing in the entanglement entropy. Another worry is that when I'm thinking about regulators, our favorite regulators, there's always, or it seems, there's typically a tension between Lorentz invariance and unitarity. I can have regulators that are Lorentz invariant, but it typically involves introducing non-unitary degrees of freedom. Alternatively, we can do things that are unitary, but we typically have to give up Lorentz invariance. And it's only when I take the continuum limit that both of these, I have to work hard to show that both of these emerge or are restored in my renormalized theory. But when I calculate entanglement entropy, I can't really take that limit. My regulator is exposed. It's sitting there in those divergences. And so it's a worry, can I really establish this for the entanglement entropy? Because those were important ingredients in the proof of the F theorem or the two-dimensional C theorem. So that's another worry. So an approach or a suggestion on how to get around all those problems was this renormalized entanglement entropy by Hong Lu and Marc Mazet. What they said is that, let's look at what an entanglement entropy looks like. And this is a formula that I wrote down before, and we're going to be in odd dimensions, so this is my new name for the constant term. And if I take various derivatives, and if I do stuff, I can manipulate this expression, and I can get rid of all of this stuff and just identify or focus in on this constant term. This was implicitly for a CFT. But if I have, if I'm at some point in the middle of the RG flow, the thing is that I should be able to organize stuff in terms of this sort of geometric expansion of, this is, again, one of the things I emphasize is this is all geometric stuff over the cutoff to some power. And all of the extra scales in the RG flows I can just by fiat absorb them into various coefficients in my entanglement entropy. And so again, even away from the conformal fixed points, these formulas will focus in and identify whatever the constant term is. This is now varying because I'm in the middle of the RG flow, but that's a good thing. I want it to change between the UV and the IR. And in fact, this is the thing that they proposed, and that was a thing, we went through it too quickly, but that was the thing that appeared naturally in the proof of the F theorem. And so that seems like a good sign. It's a footnote that, in fact, if I go to higher dimensions, they also did holographic experiments, and they found that, for example, in 4 dimensions, this wasn't it didn't satisfy monotonicity. And so there's some question then about whether this doesn't seem like a good C function by itself, but perhaps something along this line can be used. However, this idea that there's lots of geometry hidden in this formula, implicitly we're saying that we're using a very special kind of regulator, or a covariant regulator. And that's natural if we're, authors on HEP-TH. That's the kind of regulators that we think about. But one could still worry that identifying this constant is an artifact now of using a very special kind of regulator. If this is really something physical, then we should be able to use any regularization scheme that defines our continuum quantum field theory in some way. And so I'm going to argue for the F, or for this A3, that in fact, if a lattice regulator isn't something we typically use in our analytic calculations, but it's something that in principle we could use to define our favorite theory. And I'm going to argue that that presents a problem to us, because here what I have is a theory, if you like, with a finite resolution. And so this quantity, the circumference of the circle, is always going to have some uncertainty in it that's of the order of our resolution. And so if I'm shifting this number here, if different calculations shift this by things of order delta, then this stuff over here, my constant term, is going to get polluted by information coming from the UV. And so, another way of saying that is that when we get down to the scale of the lattice spacing, we don't really know what surface we're talking about, and so that's why there are uncertainties here in that circumference. And I want to emphasize that it's not just a matter of refining the lattice and working harder and running bigger codes for longer. You're going to improve your resolution or minimize or reduce the uncertainty in the circumference, but unfortunately you're always going to have a problem or a resolution problem of order delta, and here I'm dividing by that delta. And so no matter how small I make delta, I'm always going to have the same problem, that this gets polluted by UV data. And if that hand-waving argument wasn't convincing enough, here's a calculation where you put a free scalar field. I won't go into the details because we're running late, but here we're trying to identify this constant, and I'm varying the size of R, and what I see is that it's scattered all over the place, and it doesn't seem like I'm converging in any way to some particular value for this A3. And I know well, actually I don't know. When last I heard, I finally got Roger Melko to think about this problem, and of course he didn't believe me, and so he had his student working hard, but he said that he was getting similar, or they were getting similar results like this.
But if
so,
you have a large N theory where A3 is M square, and then can't I have a lattice spacing which is small, if A3 is, suppose, you've got a large number of scalar fields, and A3 will go like, say, if you've got 10 to the power 6 scalar fields,
yeah.
A3 goes like 10 to the power 6. And if you make a lattice spacing smaller and smaller, can't you actually make the correction to A6?
Yeah, the thing is, I think this is also going to expand with the number of degrees of freedom, so you're not going to get away with that. In any event, this is just a simple scalar field. I mean, you can go to, your favorite cutoff, you can do holography, and it's not a problem, but we're just saying, actually, this is, okay, I didn't say that. I probably never write it down. This is, again, work with Horacio Cassini and Marina Huerta. But we're saying that, this is somewhat unsatisfying. We're trying to establish a new physical quantity, a parameter that characterizes our quantum field theory, but we need to choose very special regulators, it seems, in order to define that quantity. Yeah. No, I can't use a lattice. That's what I just argued. If I try to use a lattice, I'm stuck. There's no way I can use that formula by itself.
This looks very similar to the imaging problem. Aliasing imaging?
Okay.
So when you get images and they get
pixelated, yes.
Yeah, and so you have a similar scale problem.
And I was afraid that Roger was smart enough. There are techniques you can use to get around pixelation. And so I thought Roger was going to prove me wrong before I ever got right up the paper, but he's saying that that's not working.
So he's saying the standard techniques for correcting aliasing don't apply in this case.
Or what they've tried anyway. I don't know. Maybe at, Pixar. Maybe at Pixar they can. In any event, I'd like to do something better, but let's establish what it is that I'm going to demand of my C-theorem, or of my physics, so that I can say I've got a proper C-theorem. So first of all, I want to say that I've identified some C function that's dimensionless, it's well-defined, and in particular, it's independent of the regularization scheme. I should be able to compute it with any old regulator that defines the continuum limit, i.e. I should be able to calculate on a lattice, if that's my choice. I also want it to be something that's intrinsic to the particular, if I'm at a fixed point, the quantity I identified is intrinsic to that particular fixed point, and in particular, I don't want it to depend on these extra scales that might go into defining an RG flow that takes me down to this fixed point. And then last of all, of course, I want the C function to be monotonic along the RG flows. It seems that with the entanglement entropy, I'm not satisfying this one nor that one. We saw examples, or I argued with the lattice that doesn't work, and we saw examples already where stuff from the RG flow sneaks into our final answer, or might, it potentially sneaks in. It doesn't, yeah, okay. So there's a potential problem anyway here. So can we do better? So how much time do I have? Really? Okay, thank you. So what we'd like to do is we'd like to think about this, a new construction, well, a very similar construction at the end of the day, but we're going to use, rather than entanglement entropy, we're going to use mutual information. So that's some other measure of entanglement between two systems. And so for two non-intersecting regions, I can define it this way. I can take the entanglement entropy of the two individual regions, and then I subtract the entanglement entropy of the union. The way I've written that formula, I stuck entanglement entropies into it. But in fact, I can't, but one can. In particular, these people can define the mutual information without actually making reference to the entanglement entropy itself. On the other hand, my my co-authors who know about this still say, well, it's not a very practical approach, and so everything I'm going to say actually uses this formula. An interesting fact that these folks showed is that it bounds correlators of operators between these two regions, so that's a fancy formula. But what's important for us is that this is a finite quantity. If I think about this formula here, turns out that the UV divergences that were associated with the boundaries of A and B get canceled by the same UV divergences, the same geometric stuff, because the boundary of A and B, or is the boundary, when I combine the two boundaries, it's the boundary of this union. And so what I'm writing down then doesn't have any of those UV divergences in it. And so if I can use a formula like that to construct a C function, I'm automatically going to have satisfied criterion one, because I've got something that's finite, that I've eliminated the UV divergences. That's the norm of the operator, and I refuse, before I finish the talk, to tell you what that means. It's not a very practical thing, as far as I know, to use in holography, but probably in quantum field theory as well. This would be of the order of the cutoff. Okay, so the claim is that our first criterion is automatically going to be satisfied, but with a little bit of work, we can also satisfy the second criterion. So here's the construction I want to propose. We take the mutual information for region A being the interior of this circle of radius RA. We take region B to be the exterior of this region of radius RB. They're slightly displaced by some separation epsilon, and I'm going to define some radius here in the middle somewhere using these equations, so that my basic variables are going to be R and epsilon. And so I write down two formulas here, but for now I'm going to, let some slack in the system. I'm going to say I'm not exactly sure where I want to put that dotted line, but I want to put it somewhere in between these two circles. These are both going to be macroscopic scales, and they're much, much bigger than the cutoff, but in particular, I want to work in a regime where the radius is much, much bigger than the separation between the two circles. And if I evaluate the mutual information for this configuration, I'm going to get something that looks like this. So here is stuff that kind of looks like what we had before. Here's the circumference, or 2 times the circumference. Before we had stuff over the UV cutoff. Here, in some sense, epsilon replaces the UV cutoff. But in any event, here's some stuff times the circumference, and then here's the constant factor. And so I want to use this C naught, or this constant factor. It's interesting. We're going to use that constant factor as our, well, that's the thing that we're going to examine or claim at the end of the day as our C function. But notice, because I didn't quite tell you where this epsilon is, I didn't quite define this C naught, because if I shifted alpha, so alpha is this parameter here, so if I move the epsilon or the dotted line a little bit, then I'm redefining what that C naught is. And in particular, I'm pulling stuff out of this term and putting it into that term. But this is stuff, this is stuff that's coming from the UV or from higher scales. And so by varying my alpha or varying the position of my circle, I'm putting in or taking some UV information into and out of this function. And so there's a problem there. In particular, what I want to do is I want to find a choice of that alpha or a particular position for my dotted line in which I know that the C naught is independent of all of these higher scales, so that I can say that I satisfied the second criterion. So let's imagine that we're flowing down to some fixed point and there's some extra scale in the problem. But we're going to choose our parameters. R is the biggest scale in the problem. Epsilon is a smaller scale. And M is some scale in the RG flow. And the reason that's a tilde is because I couldn't figure out how to put greater than or approximately 1 over M. But it's going to be, say, in the interesting case, this scale and this scale in the RG are going to be of the order of, or about the same size. Yeah, for some reason that doesn't work in my tech point, or it didn't this morning. I was tired, I don't know. So this is saying that at some scale, if I'm probing correlations or correlators in my theory, at long ranges, they're basically the conformal correlators of the fixed point theory. But when I go to small distances, I'm going to notice that some of the correlators, or there's extra stuff in the theory, and I'm going to notice at very short distances that I'm, well, there's information, or I can access higher degrees of freedom, or I can see that it was at the end of a RG flow. It didn't come out right. In any event, so in the correlations, at short distances, I see non-conformal stuff, and in quotes, I'm going to think about the high energy contribution to the mutual information, i.e. the part of IAB that's coming from these non-conformal correlators. So where is that going to be important? Well, it's going to be important, I mean, what this is talking about is correlations between A and B, but they have a limited range, 1 over M, and so it's only going to be in the vicinity of the annulus here that I'm going to get, or that my mutual information is going to be polluted by this higher scale. And in general, I'm going to get some local answer. That is that if I focus my attention in on a small box or a small piece of the annulus, I should be able to calculate precisely what that contribution is, and then I just multiply by 2 pi r to get the full contribution. So sigma naught would be the answer that I get for a straight strip. This is the first correction because of the curvature, the second correction because, well, some other curvature. And so there's an expansion like that. I can look at that formula and I can see there's the problem. This is a contribution coming from the higher scale, and that's going to create a constant term in the mutual information. So the question is, can I choose the alpha to eliminate this particular contribution to that contribution? So to make progress, or one way that you can see how to do that, you think about not this circular annulus, you think about a more general strip of some fixed width, but with small curvatures. So it's varying gently on the scale of epsilon, and so the scale of the curvatures are always much bigger, but it doesn't have to be a circle. It can be some strip that waves around. And in general, this high energy contribution, the stuff that knows about the higher scales, is going to take this particular form here. So these are the same coefficients. Here I'm integrating along my strip. N is a normal vector t is the tangent vector. Those are both unit vectors. And so this 1 over r is what? Up to a sign. That 1 over r is essentially this quantity here. So it's, I take a derivative, I see how the tangent vector is varying, and it varies in the normal direction, and so that inner product is sort of the generalization of that 1 over r. If I go to the next order, I take the second derivative and I dot it with the tangent vector, and that expression there is giving me the 1 over r squared. But now, yeah, I'll just leave it at that. If I want, well, one way to demand that this vanishes is if I have a reflection symmetry about the middle of my strip. In that case, what I would be doing is I'd be flipping the sign of n, but if I'm saying the answer is independent of that sign, then it must be that in that particular configuration, this sigma 1 is equal to 0. I.e., what I should be doing is I should take my dotted line in the previous construction, I should put it smack dab right in the middle, which corresponds to alpha equals 0. And so the claim is that well, that's the prescription. Those formulas that I had before simplify a little bit. R is now the average of the big and the small radius. I'm in the regime, though, where that epsilon is much smaller than r, and I get an answer like this. And this C naught, the claim is, should be intrinsic to the fixed point, i.e., I'm satisfying now not just criteria 1 or criterion 1, I'm also satisfying criterion 2. It's also something that one can calculate now. And so this is a calculation for a free scalar field on a square lattice. And in this case, you can see with this prescription that things are converging, and they're converging to some asymptotic value out here. Unfortunately, well, okay, I'll say it anyway. I know what the answer is supposed to be, and I'm off by some 15%, but that's because this is a very rudimentary calculation where this epsilon over r is only about 0.2. And so the fact that I'm off by that order is not surprising then. But hopefully, Roger, my friend at the University of Waterloo, has bigger computers and can run bigger simulations, and I'm hoping he's going to be trying to see how this performs when you do a better job with that. In any event, I set forward these 3 criteria. In particular, these were the new ideas that I had to worry about some of the details. And it seems that if I define C naught with the mutual information with a particular prescription for the geometry, that I've satisfied both criterion 1 and criterion 2. Of course, I still have to show you that the quantity I've picked out satisfies or is monotonic under RG flows. And at this point, well, it's about 8:30 and I have to run and grab the cab. And so I just say that the entropic proof of the F theorem, i.e. the stuff that I hand-waved before, works in this particular case. And so you can establish the monotonicity for this construction as well. So we finally came to the end. So the conclusions, the messages, entanglement seems to give us interesting new insights into C-theorems. Using the mutual information, we seem to have a proper definition or proof of the 3-dimensional F theorem. There are lots of questions one might ask. One might be, that was asked right at the beginning, how much of the structure that we saw in 2 dimensions actually lifts to higher dimensions? In particular, these folks showed that for the 3-dimensional entropic C function, that it's not necessarily stationary, and so we lost one of these criteria. We don't seem to have that using using sort of this entropic definition of the C function. On the other hand, we already saw, in fact, we already knew that was true from the 2-dimensional case. One can ask, are we focusing in on certain special cases here, or is that sort of the generic behavior? If it's a generic behavior, you know, can we find a better C function that is stationary? Other questions about, does scale invariance apply conformal dimension? Are there other lessons that we might learn about holography from this? Or can holography give us more insight into that? But more generally, I think we've just scratched the surface. We're using some simple tools that the quantum information folks have told us about. But can we use that perspective to learn more, even more, about the behavior of RG flows, about holography, or non-perturbative quantum field theory in general? And with that, I apologize for running over, but I thank you for your attention.
So, questions? I suggest we continue our discussions over coffee break. But before that, let's thank Rob once again for 3 beautiful lectures. And hope that he comes back and visits us and entertains us with more such wonderful physics.
Okay, thank you.